So now we'll take a look at lab 1, and we'll start taking a lead. So if you don't mind for 1 second, I will. What we're going to do in lab 1 is we're going to create the design for the system. We're going to run through configuring all the processor systems, all the triple timer counters that we're going to use for the pulse width modulated output, and the GPIO to provide these signals for control. So just when we come to it later on, these are the slides for doing how to connect the motor, which terminal on the motor is the positive terminal and which terminal is the negative terminal, and where we connect it to on the H bridge when we come to using the H bridge, and then how we power it. But what we'll do is we'll build the design now in Vivado, and then we will come back to these slides in the break. So let me just close that down, and open Vivado. So hopefully, hopefully if you all open Vivado, if you're following along, you should be able to see a screen similar to what I'm seeing now. And what we need to do is we need to create a new project. So we're going to go here. We're going to create a new project, and this should all be documented in the workbook as well as we're working through the workbook. So if we click on Vivado, create new project, maybe it'll come up. And then once we get a new project, we need to give it a name and a project location. Now, really important, we need to make sure that path name isn't too long and doesn't have any spaces in it if you're working on a Windows system. Hackster motor, I will call this one. And moving on to the next element of the dialogue, what we want to do is we want to create a RTL project. So we're not actually going to add any RTL in this at this point in time, but we're going to create an RTL project. We're not going to add any sources, and we're not going to add any constraints neither. What we're going to do when it comes to looking for the part that we're going to use is we're not going to click on this parts tab, but we're going to click on the board tab. And then on the board tab, if we select the vendor, it's been a little slow. If we select the vendor and select the vendor of Avnet, what we will see here is the MiniZ platform. So if we select the MiniZ platform, it will click and click on the next. We will get a new project summary for our design, which is an RTL project with no source and no constraints files added, and targeting the MiniZ board. So what we want to do then is we want to click on finish for that one. And while this project creates, so somebody's just asked a question about where the workbook is. So this should have been emailed around to you. I don't know, Katie or Tim, if we could put the link, if it's available online, if we could put a link in the chat window so as people.
I just did it. So yep, it is in there now. I will also put it in the chat. Thank you for bringing that up.
No worries. Okay. So hopefully once your project opens and loads, you should see a screen similar to this. You should see the project summary. You should see the board part down here. So you should see a picture of the MiniZ that we're going to be working on today. And what we need to do is we're going to be creating a block diagram. So over here on the IP integrator tab, if we click create block diagram, when this dialog pops up that says what do we want to do with it, we just leave leave everything exactly as it is and click OK. And this will run through. So Andrew mentioned a question actually about why additional power is needed. So we use the two inputs because the USB is limited in the amount of current it can supply. The PMIC on the MiniZ can supply quite a lot of current, and certainly enough current to drive the motor if both of the USBs are connected. But if only one of the USBs is connected, then there's a risk that we might there's a risk that we might brown out the system and have to reboot. So it's safe to have the two connectors there. So somebody's just asked what do we do if we don't have a Mini-Z board in the list? So if you don't have the Mini-Z board in the list, if you can just take a quick look at the setup instructions that we emailed to you, they'll tell you where to go to grab the AVNet board definitions for the Mini-Z for the Mini-Z, so that you can add them in and get going. So once we get to this, we'll see a block diagram just like we have below. And what we want to do is we want to add into this block diagram the processing system for the RMA9. So what we're going to do is we're going to click this little button in the middle, the Add IP button, and then in the dialog that pops up, we're going to type Zinc. And in there, that's going to give us a Zinc 7 processing system. So we're going to double click on that. Just have a quick swig. And what that's going to do is that's going to give us a processing system for a Zinc processing system. But at the moment, it's actually not configured for the Mini-Z. So it's not aware of the clocking relationships, the DDR memory that's fitted, the timing for the DDR memory. What we need to do is we need to make it aware of the board that it's running for. So to do this, we click on this block up the top that says Run Block Automation. So if we click on Run Block Automation, you'll see this nice dialog pop up that tells you that we're going to apply these settings. Leave everything exactly as it's set on the screen, and just click Run Block Automation. And you'll see it take a second or two, and it will run through. And it will apply the system. And you'll see some slight changes to the image of the symbol underneath. So you'll see now that the inputs have been removed. You'll see we've got two clocks, a reset, and we've got the DDR output there, and the fixed install. What we want to do now is to begin to start configuring and making some changes to this processing system. So what we're going to do is we're going to double click on it, and when we double click on anything, that allows us to actually be able to customize the IP. So as you can see here, we've got a nice block diagram of what's going off in the system. And we can see we've got the single core A9. We've got all the peripherals set up and configured as we need for the Mini-Z. So just to answer what Justin said in there, so block automation is actually applying so when you first put the Zinc block in there, it's not aware that the board is not aware of the settings for the Mini-Z. So if you were to open up this customization dialog, you wouldn't see any of the peripherals. You wouldn't see any of the peripherals ticked. You wouldn't see any of the clocking information set up, or any of the DDR information set up to work with the DDR memory. So that block automation essentially takes all the settings from a file that's installed when we define that we want to use the Mini-Z, and apply them to this processor to configure it correctly for how the Mini-Z's set up on the board. So hopefully that answers your question. What we want to do now is we want to make sure that the peripherals are set up as we want. So as I mentioned, we're going to generate the pulse width modulated waveform. We're going to use what we call the triple timer counter. Now the Zinc's got two of these in there, and each one of them's got three triple timers in there that can act as counters as well, surprisingly enough. And we can use these to generate pulse width modulated waveforms, which is exactly how we're going to drive the pulse width modulated waveform for our motor. And we're also, so we need to make sure that can be routed to the PMOD that's connected on the board. So to do that, we're gonna set this up to route the signal from the processor system into the FPGA half of the design. And once it's in the FPGA half of the design, we're then going to run through and connect that to the outside world so that it can connect to the PMOD on the board. And we're going to do that for the processors, for the triple timer counter, and we're going to do that for the GPIO as well. So to do that, it's really quite simple. So I'm on step 14 now. So if we click in the workbook, so if we click on the peripheral I/O pins and give it a second, what we'll see is I'll try and make it a little bit bigger on my screen so as everyone can see. We need to scroll down until we find the triple timer counter. Must be in here somewhere. The triple timer counter 0, and we need to tick to enable that. And you'll see, so these pins moving along the top are the potential positions that the output pins can be routed to on the processor I/O. Now, we don't actually want to route this through to the processor I/O. What we want this to do is to be connected to the EMIO, which is the extra multiplexed input output. And as you can see, that's showing that it's on the EMIO. So it's exactly where we want it to be. We can also double check this by going to by clicking on the MIO configuration, clicking under the application processor unit, and you'll see there that it is, if I expand this for some reason, there we go, you'll see there that it is still showing as EMIO on there. So we have this signal going in the correct direction that we want to. The next thing we need to do is we want to break out just one GPIO signal to be able to do this direction control for us. So under the I/O peripherals, we need to expand that and then scroll down to the bottom where it says GPIO. And then where there are GPIO on the EMIO GPIO, so this extended multiplex GPIO that the processor can control, but are actually connected routing via the processor, the programmable logic, we actually need to we can make that 1. So we can make that 1, and then we can click OK. So if we click OK on this, we should see some slight changes take place on the top level of the block diagram. So we'll see now we have a GPIO 0, and if we expand that, we'll see that we have an input, an output, and a tri-state. So that's to drive the output to enable or disable the output. And we also have these TTC, these 3 triple timer counter wave outputs that have appeared as well. So very simply, what we need to do now is we need to actually select one of these. And once we've selected this, we need to right click on it, and then we need to scroll down to make external. And what we'll see there is it's given us a new output pin there of just one bit output pin. And we also need to do the same for the triple timer counter output wave 0. So be very careful just to select the pin and then select make external. And we'll see that there. So if I just then click on the zoom to fit button, what you'll see is here we have the processing system, and the only things that we're putting into our programmable logic design are the triple timer counter waveform out and the general purpose I/O waveform as well. What we want to do now is we need to create some constraints, and we need to be able to start implementing the design. So to do this, it's probably a good point here to save the design. So as the design's saved, we can see this. If we want to, we can take a look at the address editor, although there shouldn't be anything in the addresses at the moment because we've not added anything into the programmable logic. Now, if we click back on here, so we have in this window here, we have the sources tab. So if we click on the sources tab, what we'll see here is this block diagram that we've created. Now, to actually implement something into the FPGA and to actually generate a bit file that we can then use in our design, what we need to do is we need to be able to create a wrapper file for this, so a VHDL or a Verilog wrapper file, such that that wrapper file can be synthesized, and then we can do the place and routing and moving on. So what we can do here is we can right click on this, if we select the design block diagram, if we right click on this, we can then select create HDL wrapper. So clicking on the create HDL wrapper, we'll get this little dialog window that pops up that says, do we actually want to, what do we want to do with this? Do we want to just create one, and then for any future references, we'll make and changes to the design, we'll make the edits? Or do we actually just want to let Vivado manage the top level of this design and do the edits as is necessary? So what we'll do is we'll click on this one and we will let Vivado manage the updates. And that means that any changes that we make, Vivado will automatically make the changes to it. It should only take a few seconds. You can see it running through there. And then we will have a top level of our design. And as you can see, I'll close that so it's slightly better. As you can see, we will have the top level of the wrapper, and if I double click on that, it will open up a Verilog file for us. And in that Verilog file, you'll see all the inputs and outputs. You'll see our two at the bottom that are our general purpose output pin and our wave output, and you'll see all the rest of the outputs actually are related to the processor system. So they're related to the DDR, the clocks, and so on that are on the heart of the processor system. So the next thing we want to do now is to add some constraints before we can build our system. We need to be able to tell it where those two pins we've just added are going to be, which I/O they're going to be added on the Xilinx, on the programmable logic half of the design. So we need to be able to say we want to use pin X and pin Y to do this. How we do this is we use the constraints in Vivado to do this. So we can click on the constraints here, and then we can click on this button here, which is add sources, and when it tells us what type of source we want to add, we can put in that we want to add or create constraints. If we click on next, it will take us to a dialog. If the file already existed, then we could put on we would enter in the we could then enter that in using the add files. But if we want to create a file like we do at this point in time, then we need to click on the create file. So I'll click on the create file and I will type in, I'll give it a name. That's the only thing we'll give it. I'll call this the io.xdc files, and we'll click on OK. So I see Pedro's got a question about what's the major difference between Vivado and Vetus, and could we not just do this lab in Vivado? And it's a very interesting question actually, because within Vivado, we're defining the hardware-based platform. So we're defining the configuration of the processor system and the programmable logic. What we're not doing in Vivado is we're not going to write that high-level software that's going to drive this system. So we're not going to be able. In Vivado, we can't write the C software that's needed to drive the processing system. So Vivado, no. So Vivado only cares. So just to answer Justin's question as well. So Vivado actually only cares about timing constraints in the programmable logic. So when you do this, all you need to do are when you create your applications. Excuse me. When we create our applications, all we need to do is create timing constraints for the designs that we put in the programmable logic. The processing system, obviously, that's hard, and that's hard silicon in there, so there's no timing constraints needed. all we're doing when we put in the process system here is we're configuring registers to give that processor system settings such that it knows how to configure, so that the software knows how to configure that processing system when it boots. Okay, so I've created a file here on my io.xdc, and I will click finish. And then we will be able to see this file under the constraints, and it will be blank. So what we need to do then is we need to add in some constraints to actually get us to use this. So we need to very carefully just check that the names haven't changed between the workbook and what were put in the actual diagram. So I'm just going to pop this out of here a second. Pop that there. Where's my XDC go? And then we need to enter these 4 constraints that are shown in step 20, that are shown in step 28. So we need to do setup, set property, and here's where everyone sees I can't type. Package pin M15, and we need to tell it to get the ports of the pin name TTC wave 0 out underscore 0 TTC wave 0 out underscore 0. We also need to do the same for the GPIO pin that we've defined, so that's on L15. That's a good one. Somebody spotted my typo already, so it should be wave 0, not WAV 0. And yeah, somebody else was asking. Nitin was asking about can we use multi-cycle timing path constraints? And yes, you can use multi-cycle. You can put multi-cycle timing path constraints in there and false path constraints in there. You're going to find a lot of, as you start working with Vivado, you're going to find a lot of clock domains. So you'll come across these quite often. Quinn asked a question about what did Vetus, does Vetus do what Eclipse did pre 9.2? Yes, it does. Essentially, you'll see that when we get to it in a little while. But yeah, in the in sort of 2019.1, if you used SDK, you'll see that it created the board support pack, the hardware, the board support package, and the application. What you'll see for the embedded flow in Vetus is very similar. It's just slightly different in the hardware definition, the board support package, and the first stage bootloader are all grouped together in what it calls the platform, and then the application sits underneath the system platform. But it's very similar to what you might be familiar with. So let's just put this one in here as well. So that's going to sit on L15, and we're going to do get ports GPIO 0 0, and that's correct. GPIO 0 0. Now, once we've also told it what the pin types are, so the pin types that the pin locations that we've got, we also need to tell it that we also need to tell it what the voltage banking of that I/O is. So we need to tell it that it's an LV-CMOS 3.3 volts in this case. So I'm just going to quickly copy and paste these two, put them under here, and then I'm going to use the I/O standard this time. I/O standard LVCMOS 33. And then hopefully this should be the constraint. So it will tell us where we want to put. It will tell us where we want to put our. Tells us where we want to put our pins, and it also tells us where we want where we want to, what type of I/O standard that those pins are on, such that it can check that they're correct. I just want to have a quick sanity check of all that and make sure that is okay. And that is the same as what's in the top level. And that's the same as that's in the top level source there. It is. So we should be good to go now. So we've got all our programmable logic design in and completed, and we can then begin to generate our bit stream. So if we click on generate the bit stream, if you've never done this before in Vivado, the simplest way to do it is to click on this generate bitstream button here. You might get a warning about there being no implementation results available because I've asked it to generate a bitstream and allow it to run through. But in that case, there's nothing available, so that's fine. So we can click on it to run through. And what we should see is it should prepare to run through and generate the bitstream. Now, depending upon the speed of your computer, the number of cells the number of processors you actually dedicate to this, to running the tool, will determine the amount of time that it will take for this to run through. So what we'll do now while this is running through and generating is we'll come back to our hardware build, because we're running a little bit ahead of ourselves. So we will run through and see what questions we've got that we could answer. Done that one, done that one, done that one, done that one. Okay, Frank, you're still having problems looking for the board package for Vivado. I don't know where the chat window is, if we've got the chat window available. And I think if I pull up the setup instructions very briefly on my screen, shows you how to install it all. Okay. So the way to get these, to get the files is I will pull them up over the break for you, Frank, so you can still get them. They're not included. The mini-Z files aren't included by default, and Tim's just put the link up there, so it's to the GitHub avnet.bdf. And literally, you just copy and paste that into the boards area of your Vivado installation. So it's relatively straightforward and pain-free to do. I had a typo in my XDC file generate bitstreams. It will take a few seconds to cancel. Sometimes normally it kind of finishes the step it's doing, and then it moves it back to stops the compilation there. While this is building, mine's running through. So it's going to run through. I didn't touch on this actually, and I should have done. When we implement the FPGA design, or when we implement design in programmable logic, this should be fairly fast because there's not actually much being put in it. But it goes through 3 stages essentially, and those stages are: it will go through the first stage. It goes through synthesis. Now, synthesis is actually taking the VHDL, the Verilog netlist that's created, and actually turning that register transfer level description into lookup tables, into logic resources. So it's converting them using skills into get the correct Boolean equations. So it's converting these into D-type flip-flops, DSP elements, block RAMs, into lookup tables and so on. That's what synthesis does. It gives us the actual logic design of the circuit targeted for the implementation with the device that it's implementing. Once you've got a logic level netlist with all the cells mapped to what's in the tool, the next step to do is then it's actually got to place those logic cells within the device in the available logic cell locations. So it will run around and it will place them within the FPGA. Now it will then, once it's done that placement, it will then try to connect the routing them all together and connecting them all together at once, connect the cells together as they should be in the design. Now that's where the timing challenge comes in, because depending upon where you place these logic cells and the frequency that you want them to run at, and the length of the routing that's in between functions, that leads to timing issues and timing errors that you're trying to do, which is why defining sensible constraints and having a sensible approach to placing and routing and defining your constraints, but not overly defining them, is a very good way to get your design to achieve time enclosure and will actually allow you to deliver to your customer. So Amit's just asked a question about, okay, someone was just asking a question about which board they'd recommend for doing machine learning and AI. And there's a number of boards about. The Ultra 96 is really good, and I think Xilinx has one, the ZCU 106 and there's 104 are also really good for doing that with the Xilinx DNN DK. Could I show one more time where in Design One Wrapper I can see the constraints file works? So it was just so you'll not really know that the constraint file works until the design is actually placed and routed and it's actually run through. You can see now mine's now running the bitstream, so provided I've not got any typos in there, that should be okay. What I was doing when I was looking at the Design One wrapper was I was just doing a quick sanity check that these two outputs down the bottom had got the same names that I had used within. I'll come back to that in a second. We're using the same names that I'd defined in my I/O constraints. My bitstream failed with no constraints selected for right. Amit, I'm not really sure what that error is. If you could just pop a thing in the chat, I'm sure maybe Tim can help me take a look at it. So it's really we'll try and get you running with that one. So now this design's actually placed and routed. It's run through, and we've got a design that we can take a look at it. A VHDL file, Quinn, is going to make no difference whatsoever whether you've got VHDL or Verilog. It's just literally the file that's going to be synthesized. Being in Europe, I'm a VHDL guy, not a Verilog guy, but I often forget to set to change it from Verilog to VHDL, and I've never really hit any problems with it. So now our design's been implemented. We're in a stage where we can move on to do the software development. But what we need to do first is we need to connect and build together the H bridge and the motor. So for that, I'm just going to flip back to the slides now and just pop this one up if everyone's okay with that. So what we'll see here, I'm just going to turn the camera down away from me, perhaps a little bit to my desk, maybe. How does this work? There we go. So we can see I have the Mini Z on the, so I make sure we don't run over into the break. I'm sure Katie will tell me if we do. So we've got the Mini Z. I've got the two power cables. If you're a Brit following along, then for the best Blue Peterwood edition, I've got one already built up and ready to go. If this is the first time you're building it, what we've got here is the H bridge. So you'll see here we've got the connector that we're going to connect it into the PMOD on. Shockingly bad here for ESD, by the way, my behavior. And then we've got some additional pins here. On the additional pins, if you look, you'll see that one of these is marked VCC and one of these is marked ground. And of course, we've got the motor with our two terminals on it. And looking at it this way, we will see that this terminal is the positive terminal, and this terminal is the negative terminal, I hope. So if you have a pair of pliers, wire strippers, what we need are three little cables. Now I think some of you got these supplied when you do the kit. So we have one that's female to male, and then a couple of others which are male to male. And what we're actually going to do is we're going to use this. The first one we're going to do is we're going to use this female to male one, and we're going to connect that onto the VCC terminal on the VCC terminal on the H bridge, and then we're actually going to connect it to the screw terminal using a little screwdriver. We're going to actually connect it onto the screw terminal. No, we're not, because what I'm going to do is I'm going to actually snip the wire off, because this one's not a male to female, it's just a female to female. What we're going to do is we're going to snip the end off if it's a female to female, or if you've got a female to male, then you don't need to do that. Just literally going to take snip the ends off, create a little bit of area on the cable, and then I'm just going to tuck that into and fasten that into the VCC terminal on the PMOD. So hopefully you can see me doing that and pushing it in and then screwing it in. So how's everybody's builds going? Is everybody making progress, or anybody having any issues I can help with while we're trying to get there? So that's the first one that we're going to do, and then we're going to do a similar-ish thing with the two other cables. Somebody's just asked a question. Can the SOC FPGA start without setting up the PS, but instead only by using a microrelay? Actually, no, it can't. So in this system, in the Zinc system, because the processing system is the master, that is the one that boots and configures the programmable logic and configures the system. If you're debugging and you've got a JTAG link connected to it, and you just want to download over the JTAG link into the programmable logic design, you can do that. But actually, for deployment in the field, you're not going to be able to do that. Okay, because we're doing the logic, it is in the PS anyway. Yeah, Quinn, all the logic for this design, the triple timer counter and the GPIO, it's all embedded in the processing system. How to connect to a stepper motor through the Micro Z, Mini Z. So that would be a very similar example, depending upon the interface of that stepper motor. So whether it's a DC motor like this one, or whether it's a servo motor where you're driving in a PWM waveform, you can do that. It's not such a limitation of the chip or the board. It's more to do with the architecture of the chip itself. either the programmable logic or the processing system has to be the master and do the configuration and the booting, and to be as close as possible to a traditional software flow. The processor is the master in the Zinc and the Zinc MP SoC chips. So with that first cable kind of connected in there, what I'm going to do for the next two is, even though they're the same color, is I'm going to connect one of these terminals into the M plus and fasten it in to the terminal. And then I'm going to snip the top of it. Strip the cable. Now, I'm not going to do this because I'll do it live. If I do it live on air, I'll probably manage to burn myself. But in the original version, if anybody wants to, it's better to solder on these terminals to the motor. So I'm going to connect the positive motor terminal to the motor, and in this example, I'm just going to literally just wrap it round the terminal tag, feed it through the terminal tag, and then just wrap it in. And hopefully that should be sufficient for this example. It's not the greatest connection in the world, and if you guys have got soldering irons that you want to try and solder it in with, then please feel free. Take a snip there. Can I click that one off there, and then do the same with this one. So again, just sort of tighten up that loose end there. Plug that into the motor negative terminal. And when we come to demonstrating this later on in the actual lab, I am actually going to use the pre-built one I made earlier, just to make sure that it's the same. And it's no problem. So both of those screwed in. We've got the VCC screwed in there, and then literally again, just going to wrap that, feed that through the hole in the eye on the motor. And wrap it round again. So that should give us, hopefully everybody can see that, that should give us the motor now all connected up to the PMOD. I don't know if that's actually going to focus on the PMOD or not, but we can go through that over the break as well if people want to do that. So are there any questions? Are there any other questions that I've not? I'll turn this up to myself now. So are there any other questions that we've not got to yet as we're working through this hardware side of the design, as we're a little bit ahead of ourselves, so we can start with the Q&A if that's okay. Katie, for the first half.
Yeah, that sounds great. So I think there were still some issues. Frank is still having some trouble finding the BDF file for the 2019.2. So I know that BPF. Was that was the link that Tim sent earlier?
It was the link that Tim sent earlier, yes.
Okay. So he's saying that it's for 2017.2, not 2019.2. So I don't know, Tim.
Oh, so let me just click on that link that sent. I'll just scroll up to it and find it. Where would it be? avnet.bdf. Okay, and then maybe I can, where's my mouse gone? Pull that down and pull that down there. Okay, so it should be on the master tag of the branch there. And then if you'll see the, you'll see the mini Z there. Don't worry about the fact that it says 2017.2. it's literally just an XML file that sets up the Vivado. So that was obviously just the version that they created it and issued it in first, but it will work in all the other versions. So it will work in 2019.2 as well. So you just need to copy that and paste it into I think Tim gave a directory location as well as to where to copy and paste it.
Great.
So you put that into, once you've downloaded that, you can, if I just open up my computer for Explorer for the time being, just literally extract that, download it as a zip, and then extract the zip into a window, into a folder, and then you literally store it under your Xilinx installation, and it will be under Vivado 2019.2. This path depends upon where, up until this point, it depends upon where you've installed your Vivado location. But you will put the files under data board files, and you'll see the list of them there that I've got installed on my machine. But literally just copy and paste that top level PDF file under there. Okay, so Quinn said he's got a problem with the synth module. Not found. What's the name, Quinn? What's the name of your top level diagram? If you go into this block diagram, does it say processing system _7 _0 there, or is there a different name?
Yes.
So did you save, Quinn, did you save the project? If you could just say, whether you save the project or not, it might be worth actually as well in the block diagram, just clicking on the validate design, excuse me, just to rerun it, and hopefully you should see something that says there are no errors or critical warnings. But if there are any errors or critical warnings, let me know.
The icon is gray, it sounds like.
Icon is gray, validation. Oh, you're using 19.1. So this shouldn't be a direct issue of using 2019.1. It shouldn't really make much difference. The flow will be slightly different when we use SDK, but it's not hugely different. I wonder. I'm not going to do it on. So when you look at your design, you have this structure that appears where you have design one wrapper, design one processing system showing there. Or do you kind of see a question mark or somewhere along the line? Yeah, if you could paste a screenshot, that'd be wonderful. If you can, I don't know if the tool allows you to do that, but if you can, yeah, that'd be wonderful. And we'll take a look and try and do it. How's everybody else doing? How's everybody else's design kind of run through and built now? It's fairly straightforward. And have they built the little mini Z motor control?
Looks like I haven't heard anyone say they're too far behind
No, well, that's good. Normally everybody's saying, "Can you slow down, please, Adam?" So
I did get a question asking if you could show the motor connections again.
I've just seen it. So I'm going to put that up. I will put that up again while Quinn's trying to work out how to show me a screenshot. So I'll put that one. I'll put that one up there. So essentially what we're going to do, we're looking at this, hopefully you can all see my screen. What we're going to do is we're going to connect from the pin that says VCC from the header pin that says VCC. You're going to connect that into the terminal that says V motor, and then you can connect the motor positive and the motor negative to the motor. And if you look at to work out which way around the motor is, which one's the positive and which one's the negative, because it's a little confusing. If you look at it with the end on, with the plastic end, the side to your right will be the positive side. So it's all flipped around, but this is the positive side and this is the negative side if you look at it end on. And what it should look like when we finished is it should look something roughly like this. Quinn, I don't know if you can post me a screenshot or not, but if I pop you my email address in the chat window, if you can't post a screenshot, you can perhaps send me the email. You can perhaps send me an email with it in. Okay. Is there any other? Okay. Oh, Google Drive. Maybe that will work. I can't select it.
Adam, you wanted to share your email with everyone, right?
Yeah, I don't mind. It's all over the place.
Okay. You just sent it to all panelists, so I'll go ahead.
Yeah, I figured that. Sorry, but if anybody has a question, if anybody has any questions or anything after this, then feel free to reach out and send me an email. I don't know how you do this, Katie. I don't know if it's possible. I can't seem to select the text in that answer.
Yeah, it doesn't work. It might actually be better, Quinn, if you send that link to Adam in the chat. I think that might actually have a link. For some reason, in the Q&A on Zoom, it doesn't allow you to copy and paste.
I think. Let me try.
There you go.
Ah, perfect.
How's everybody else doing on their builds? You can just type that you're doing well or need more time or want to go back to something in the chat. We can revisit anything.
Okay, we're all ready to. Okay, so Frank needs some time. So we have a little break coming up anyway of sort of 30 minutes in a few minutes time. So that'll give you sort of running a little bit behind. That'll leave you a little bit of time to catch up, and then we can start. I'm not going to disappear anywhere. I'll stay around for the break anyway. So if you've got any questions, then feel free to shout out and ask them me. That is really odd as to why you get that synthesis error. What could that be? Okay. Could you try, Quinn, on the, if you expand your design sources in that sources window, so as it looks similar to what's shown on my screen now, do you want to try hitting this button? I'm not going to do it because it'll reset my configuration. But if you click on the reset output products and wait for that to complete, and then right click on it and click on generate output products, and perhaps give it a try again at synthesis once that's done. No, I don't think it is, Quinn, that your module starts with design one, because that's actually the name of the diagram. If you expand it. So if you want to do a reset, Quinn, what you could do, I'm not going to hit enter, but if you come down into the Tickle console and type project_reset and hit enter, it'll remove all the configuration data and everything, so you can start running from scratch. Okay, that's that done. So somebody asked, what's the difference between Vetus and normal SDK? So if you use the normal SDK tool that Xilinx had prior to 2019.2, what you could do is you could do embedded systems work with it. So by that I mean you could do your creation of your board support packages, your first stage bootloaders, you could write your application for bare metal, for FreeRTOS, and you could of course use it for Peta Linux development, application development as well. What you couldn't do though is actually, what you can do with Vetus is actually take a C function that you've got in your running in your software, and actually pick that function up and move it across to being run in the programmable logic, and accelerating that into the programmable logic using the OpenCL framework. So that's what Vetus gives you, is it gives you the ability to use what they call the acceleration flow, and take the data, and start putting C functions in the spare programmable logic that's there, and running it through. It requires a little bit of different setup to what we've got here today. But we can. But if you follow my blog, then you can see several examples of how to do this. Not actually on the Mini Z, but actually targeting the Micro Z. But it's exactly the same. It's the same sort of device, so the steps are identical. So somebody just asked all the panelists, how difficult is it to create board support files? By board support files, an interesting question. What do you mean? Do you actually mean the sort of like the board support package that runs on the software that allows us to run our application? Or do you mean the support files that kind of configure the device for a particular board, so like a Mini Z or a Micro Z or an Ultra 96 or your own custom board? So somebody was asking about what's more efficient, about a PS or bare PL, or maybe combined. So this answer is this system is it's just mostly using the processing system with a slight bit of routing in the programmable logic. And it really depends. It's like anything. It really depends upon the application that you're trying to address. So this approach is really quite good and a very scalable approach, because obviously we can easily run up to six motors from the triple timer counters in the processing system, and then actually we can add as many more as we want of those within the programmable logic. So we can put PWM counters in the programmable logic, and we can scale up. And the only real limitation is the logic resources that are in the design and the number of pins that are on the FPGA, of course, to route those outputs out. So I think this is why we propose this project. So I think it's a good example of showing you what you can do with these heterogeneous system on chips, and how much resource it actually leaves for you to be able to run through and then add in your actual functionality or your algorithms within the programmable logic or the processing system. Quinn, do you know if your design built yet, or are you're still struggling with it? So just to come back to that question about creating a file for a customized board, it's actually quite simple, because as Tim was just saying, they're just XML files. What you can do, if I just open up my system for a time, if I open up the Zinc for a second or two. So you can obviously configure your system via entering information here. So you can enter information on the clocking structure, on the MIO configuration that you want, on the DDR configuration as well. You can also export that information as well. So you can export configurations, and you can get that written out as a XML file, as Tim was saying, so that you can pull this into your custom design. Okay, Quinn. So the problem with that is you've not quite completed your constraints file. So you might have put the package. So can you just check that you put the package pins in there, but you've also set this IO standard here, so that it's actually set it to the right VV3. Just go back to your diagram a second that you just sent across.
Adam.
Yep.
It's 9:30, so I think that's officially our break time. So I was going to suggest we keep answering questions, and then just plan on moving to lab 2 at 10.
That was my plan.
Sorry, in a half an hour, depending on where you all are located.
Yes, that was my plan. I was just going to run through these questions that are open, and then and then if people have breaks, they can have breaks, and we'll carry on at
excellent
30 minutes, which is 10 a.m. your time, 6 p.m. my time.
Yep. So 10 a.m. PST, if you guys are wanting to compare that to your own time zones. One of the questions I did just get was if it's possible to receive a copy of the Q&A session. Yes. So at the end of this event, it'll probably be, a day or so. We'll send you a follow-up email with the recording information, the slides that Adam has up here, and a copy of the Q&A. So if there's questions that you have in the Q&A that you want answered, definitely make sure that you put them in the Q&A. We're trying to answer the ones in the chat too, but it's hard to see them all. So if you have questions, make sure that they go in the Q&A so that we actually see them and make sure they get answered before the end of the event. Also, Adam, as you are answering questions, if you do decide to answer them live, if you hit done, once they've been answered live, they'll go away, and then we won't have to worry about answering.
I've been clicking answered live. I forgot to click done, so we might have to.
That's totally fine, but that'll help us to see which ones have already been answered as well. All right, so I think that's it. So if you guys want to, grab a snack or anything like that, you're welcome to do that. Adam's going to keep answering questions, and we'll be back here in 27 minutes.
Okay, so somebody's saying the project standard, the project page on Hackster, and the examples given in this webinar might be slightly different due to some IO naming, and that's the case. What else have we got? Quinn looks like his founder should end in a Z, not an O, so hopefully that will work. Robert, yes, you do need both. Hopefully that should come up to that one. So somebody asked what Peta Linux is. I was just looking for that question. Where did that question go? So somebody asked what Peta Linux is. Peta Linux is an embedded. Well, as Robert said, Peta Linux is great, and it runs under Yocto. It's essentially embedded Linux running on the ARM-A9 processor. We're not using it today, but if you want to use some of the more advanced features on the Mini Z, like the Wi-Fi and the Bluetooth and such like, then it's better to use the communication stacks and everything that comes with Peta Linux. You do need to use obviously, because you're building a Linux kernel and file system, so you need to use a Linux machine or a Linux virtual machine to get that up and running. So Andrew asked, what about where the output of timer pin 0 is directed to? And that is directed to the pin M15, as you can see in the constraints, and it's in the lab guide, hopefully. To the guy that asked about if you can do it via a Mini Z via remote control via a phone, yes, you could if you spent the time to get the Bluetooth on the Mini Z up and working, and then you could control it over the Mini Z over the Bluetooth from your phone. I'd not connected to. Somebody was asking about connecting the Mini Z up to the power stuff, and I've actually not connected all that up yet. I was about to do that after the lunch, after the break. Somebody asked if I can speak about the DPU and the DNN-DK, and I can. So the DPU is a deep learning processor unit that's actually embedded, that's put in the programmable logic side of a Zinc or a Zinc MPSoC, and it allows you to take your AI examples, so your Caffe, your TensorFlow, and it allows you to run those on the Zinc systems, and it allows you to, and by doing that, obviously, because you're leveraging the programmable logic side of things, you get a much faster, more deterministic response. You get a higher improvement of throughput on that. So the DNN-DK is the Deep Neural Network Developer Kit. I think that's actually being replaced these days by Vetus AI. So if you go and take a look at Vetus AI, you can see that it will give you everything that the DNN-DK did, but it ties into the Vetus framework. So you'll see the optimizer, the profiler, the quantizer, and all integrated with the XRT runtime and the DPU. There's also a model zoo that's been supplied by Xilinx as well in that, so you can get models for training into the for training in Caffe and TensorFlow and so on. So Robert said Pet Linux is great. It runs on the Yocto, but no, actually, it will run on the Zinc as well. So you can target the Zinc. It will even run on the Microblaze as well. If you use Microblaze, you can run Pet Linux on the Microblaze. If you're curious about how to do that, I've mentioned it once or twice, but I write a blog called the Microsoft Chronicles on how to use Zinc MPSoC, Xilinx devices, and you can find quite a comprehensive write-up there of how to do that. Okay. John, so we've just had another gentleman, another attendee, actually have that same problem with the synthesize module not found. If you try resetting, if you right click on the design here, try reset output products, and then wait for that to finish, and then click generate output products, and then try rerunning it. Hopefully that will make you have a little bit more success. Robert, did you get your Mini Z to power up with this board connected to it? Amit, would VT support the Ultra 96? It will indeed, yes. One second, let me have a look at that Quinn for you. Oh, okay, I see what the problem is on your one. In your XDC file, you've got an underscore. So you've got an underscore here, Quinn, in your XDC file, which is not the case. So you just need to remove that, and then hopefully it will run through. Rafiq, I'm not sure if there is a we can actually, if you want to create the XDC file, let me show you a different way that you can do that, since we've got this running and we're into the break anyway. So in my design here, if I go and open the synthesize design, now obviously when I've synthesized the design, if I'd not written any XDC files, if I'd not written the XDC file, I could get the tool to synthesize the design, but it won't place a root because it doesn't know where you want to place the I/O. But in the synthesize design view, if you go to view, If you go to layout and click on IO planning, it will bring you up a list of all your IO ports in there, and it will bring you a list of the what it calls the scalar ports and the GPIO ports. So you can see here we've got our two GPIOs there. We've got the GPIO, we've got the triple time encounter wave, and these are on L15 and M15 because they're coming from the constraints file. If you didn't have a constraints file in there, you can just use this package pin to collect it, to select the pin, and then when you click on save, it will ask you for the name of the XDC file that you want to save it into. So if you don't have an XDC file, it will create one and save it for you. If you do have an XDC file, it will append it into that one. So somebody's asked if we could implement a H bridge on the PL of the mini-Z and use that for motor control in real time. Essentially, the H bridge it's high power electronics, so it's not something that we could put internally in the FPGA. The real-time control will come in this application as well, just by using the A9 processors, because we've got, well, as you'll see in the code, we've got a interrupt-driven system, so it's fairly responsive. If you wanted a little bit more responsive system, if you wanted to be double certain it was working, you could create the pulse width modulation circuit in logic and implement that in the programmable logic, as opposed to using the triple time counters under software control. But that's about the easiest way to do it. Unfortunately, you're not going to be able to implement the actual H bridge itself in the programmable logic. So somebody's asked if I could write comments next to each line of code. We've got quite a lot of code coming up in the next one. So I probably can't do it at the moment because we're just going to be doing some copy and pasting to make sure that we can achieve the time scale here, because we've got sort of 30 minutes or so when we come back from the break to get this up and running. But what I will do is I will talk about it as we go through. Feel free to ask me questions. And then after the call, after this class, I'll go through and I'll put some more comments in and get Katie to share it around. Somebody's just asked, Carfix just asked if it'll be in the next issue of the Microsoft Chronicles. It actually, so there's a project already existing on my Hackster channels, which is in a little bit more in depth than and a little bit slower than me talking. That's already there, and a lot of the techniques that we're using today, the triple timer counters and so on, they are all in the Chronicles. Justin's just asked about the Alveo line. And the RTL background. I think that's the same as well. So that the card, essentially, the card for Alveo is an external accelerator that's always assumed to be, it's running with a host in the open, because it runs around the OpenCL system. So it's talking to an x86 host or something, and the card is the Alveo card is the accelerator. So again, the processor system in that is always the master and boots it up and gets it running. Yeah, so yeah, I guess just coming back to that one, yeah, the Alveo card really is designed to sit in data centers where it's connected over a PCIe link to an x86 type processor, and the software is developed on the processor, and then which is in the OpenCL world is the host, and then you have the kernels running on the Alveo cards to give you that acceleration. Yes, that's exactly the x86. Justin in the question saying that. So the x86 host communicates with the Alveo programmable logic via PCIe. Yes. So in the Alveo cards, there's no Zinc. It's actually just the FPGA. It's just an FPGA. As I understand it, anyway, it's just a programmable logic FPGA and not a heterogeneous system on chip. So it's just communicating with the FPGA over PCIe. Adam, can I recommend some sources with examples about timing constraints in Vivado? You know, there's this really great blog called the MicroZ Chronicles, and that's got some examples of timing constraints in there. And to be honest, the Xilinx user guides as well are actually pretty good on that, and the ultra-fast design methodology is really quite good as well to take a look at. So Quinn, no, I don't have any experience of open source things like Clear for Light and how it's using it. I'm just kind of basing it off my engineering knowledge and experience over the years and saying, yeah, you could kind of do this with this type of application. How's everyone doing? Everyone kind of getting there? Robert, you're getting a cannot get memory read error, cannot help processor. It might be worth hitting the reset a couple of times on the MicroZ to get that up and running. Can't say I've seen that issue before, but if it persists, we'll try and get you up and running with it. Quinn, I'm really glad that finally built for you. So Frank asked about how to use SDSOC in Vetus. So SDSOC is no longer really, Vetus replaces SDSOC. So I think at the last issue of SDSOC, and Tim obviously worked for Xilinx, so he knows better than I do, but I think the last issue of SDSOC was the 2019.1 version, and moving forwards it is the Vetus OpenCL flow that you'd use. They're both very similar, but there's a slight subtle difference in between the two. So Amit's asking if you should save the motor control code provided in the link. And yes, yes, you should. If you can just say copy and paste that into a blank text file and save it as a .c file or a .text file, that's fine. That'd be wonderful if you could do that. So somebody's just asking a question about how in avionics FPGAs can be used. So there's quite a lot of there's quite a lot of areas that we can use avionics for FPGA. So they're using a lot in sort of control systems, in radars, communication. So it's quite a diverse area. I think you'd be surprised just how many FPGAs are sat in aircraft today, and of different types or in different uses. Obviously, when you want to use them in avionics, you've got some considerations such as DO254 to make sure that the design's nice and safe, and you're not going to have any impacts on the design. But they can be, they can be mitigated. I mean, if you want to know a little bit more about it, if you take a look at my my website, my company website, aduvioengineering.com, you'll find a couple of, I think you'll find an hour's talk that I gave talking about how you can use FPGAs in mission critical systems, which includes avionics. Hi Fred, so when you ran through this project yesterday, I think you probably connected it up to the tri-state output, not the output. It doesn't matter, it's probably just a finger click issue in Vivado, but hopefully it wasn't too bad an issue and still worked for you. Linux on the Mini Z. Can I just make a comment to everybody, and I'll make it again that we when we start again. But when we plug the H bridge into the PMOD 1 slot, make sure that the Mini Z is not powered when you do that, just to make sure that there's no risk of any issues or any damage. No, I've not seen the one about the voltage failing. Robert, when you try this with your design, do all the lights come on? Does the ready light come on? The PS and the PL light come on, and the power LED come on? So Anton, talking about writing a clear guide for Pedal Linux. Yes, there are some to work with the XDMA, VDMA, and so on. It is possible to write it and build it in the Vitis environment. You might want to take a look into, actually I'm going to tell you to take a look into a thing called Pink, which is really quite useful for testing, for maybe not for when you want to deploy it, but it gives you a real lot of information for being able to test and deploy, test DMA and VDMA structures. There are also a few other links that I can think of, but I can't drag them up right now. But I'll pass them over to Katie, and she can append them to the answer. Okay, Robert, so we're not really going to be using Pedal Linux. So if you want to prevent Pedal Linux from booting, you can just flick the switch on the bottom to boot from the JTAG, not from the flash, but I suggest you power off your board first. Andrew asked where the PS package pins can be found. So they're all by default. They're all hard defined in the silicon, obviously. They're defined in the user guides for the IO user guide for the Zinc 7000. I can't remember off the top of my head what the reference number for that is. I know the user guide is 585, so that might tell you some information. That'll tell you some information as well about which pins, excuse me, which pins are allocated to the PS and which pins are allocated to the PL. Okay, Amit, so you just mentioned that you've opened the implemented design and see what the implemented design is showing. So let me just open that on my screen here, and I will show you. So first off, you're not going to see an awful lot in this design because we've not really put much, well, if anything, in the programmable logic. But what you can actually see here is we have this is the processing system essentially, and then these are the 4 logic regions that exist in the Zinc 7000 and 7. So on this side of it, under the net list, you can see the net list, you can see the nets that exist, you can see the leaf cells that exist. So if I click on the GPIO and the waveform buffer, I can possibly highlight these as we can see them. Maybe we can see them in the design, maybe not. And then in design 1, we can see the leaf cells as well. Although there's really not a lot to actually show because we've just literally routed 2 inputs through. But if you had an actual design in there, you could a logic design, you could actually run through and identify and highlight nets and highlight logic structures. And that's really quite useful when you've got some timing constraint issues and you want to perhaps consider the placement of logic cells, whether they're closely related or whether they need to be a little further apart. You can also see all the things such as timing information. Here it will give you all the information on timing, worst case negative slack, holds, and so on. And you can also see the power budget as well. So let me just pull that up a little bit, and you can see the type of power it thinks we're going to be pulling in this example. And it'll also give you a confidence level somewhere. You should be able to find a confidence level in there as well to tell you how confident it is in that power summary. You obviously can find all the reports as well, and the tickle and the log messages. And if you want to, you can start taking a look at some of the clock reports, the clock interaction reports. So if you've got different clocks that are on different clock domains and you want to see their interactions, so you can start doing a little bit of making sure you've got clock domain crossing correctly, you can do that there. And you can take a look at the power report, the noise report, and run the DRC. The DRC is important if you run things, well, the DRC is important anyway, but the DRC is really important if you're doing anything in avionics or something and you want to make sure there's physical isolation between blocks in the logic and you use the isolation view. So hopefully that answers your question. So Darshan, I don't think FPGAs are really being used for deep model for training. I think they're really used for inference, and that's where they really show a benefit, but they're not really being used for training those networks. And Darshan, again, FPGAs are quite good. I'm not going to get into the FPGA GPU, which one's slightly better debate. Again, it depends upon your application, what you're trying to do. In a lot of cases, you'll find that the FPGA outperforms the GPU. But as engineers, our job's to select, obviously, the right tool for the right job.